In this video, I'd like to review inverse trig functions. First off, what is it? Well, let's remind ourselves of some of the basic trig values. For some reason, 0, 30, 45, 60, and 90 are important. Or in radians, because we're grown-ups, we use radians. 0, pi over 6, pi over 4, pi over 3, and pi over 2. Here's a table. You can pause it and copy it if you'd like. So let's find the inverse trig functions. First off, when you find inverses, algebraically, you switch your x's and your y's, and then you solve for y. When you do that graphically too, you switch your x's and your y's, which effectively reflects this graph across the line y equals x. So let me take my sine graph, and I'm going to flip it, and I get something like that. Now, obviously, this is not a function. It fails the vertical line test. It's all over the place. I only want to choose a chunk of it that represents a function, and a pretty chunk of it. So the chunk I'm going to choose is the section that straddles 0. Because 0 is a nice number. You know, we got plus pi over 2 to negative pi over 2. It's a nice chunk to look at. So I'm going to rewrite it so it's really not in scale, but that's okay. It gives me a better idea of what it looks like. Arc sine of x equals y if and only if x equals sine of y. So what does this mean? So I know that sine only spits out numbers between negative 1 and 1, which means the domain is only going to be between negative 1 and 1. Our range is going to be between negative pi over 2 and pi over 2 because that's what I restricted ourselves to choose the right hump of our sine graph. Example. Sine of pi over 3 is the square root of 3 over 2, so I know that the arcsine of the square root of 3 over 2 is pi over 3. Let's put this little chart up to remind ourselves about those values. Let's do another one. If I have arcsine of 1 over the square root of 2, that's pi over 4. I can go over here and look for 1 over the square root of 2, work our way over, I get pi over 4. So arcsine of 1 over square root of 2 is pi over 4. If I have arcsine of negative 1/2, I'll go down the 1/2. I see that it's pi over 6, but it's negative, so I have negative pi over 6 radians. Sine is really nice that way. If it's arcsine of a positive number, the answer is positive. If it's arcsine of a negative number, it'll be negative. Here we have the tan graph. The little dashes are our asymptotes. So if I switch that across the line y equals x, I get something that looks like this. I'm going to choose, again, the one that straddles 0 because that's the nicest one for me. And looking at that graph over here, I see my domain is the reals. My range is between negative pi over 2 and pi over 2, where those asymptotes are. Arctan of x equals y, if and only if x equals tan of y. The domain is the set of real numbers. My range is between negative pi over 2 to pi over 2, not inclusive because it'll never actually reach pi over 2 or negative pi over 2. Let's look at an example. Tan of pi over 4 equals 1, which means arctan of 1 is pi over 4. Arctan of 1 over the square root of 3, so I go over here and look at 1 over the square root of 3, work back, I get pi over 6. If I want to know the arcsine of negative square root of 3, I'm going to look for the square root of 3, work my way back and see that it's pi over 3. Since I'm asking for the arcsine of negative square root of 3, the answer is negative pi over 3. Cosine is a little bit more of a pain in the butt. Notice I'm going to flip the graph, and it's still not a function, but I can't zoom in on that section at 0 because I'll only get positive numbers here, and it's not a function because it fails the vertical line test. So I need to choose a different section of this graph. I'm going to choose from 0 to pi. Drawing the graph of that, I get something that looks like this. As before, arc cosine x equals y if and only if x equals cosine y. My domain, again, is going to be between negative 1 and 1, but this time my range is between 0 and pi to make sure I get all the values. Let's look at an example of how this can get a little messy. Cosine of pi over 6 equals the square root of 3 over 2, which means arc cosine of square root of 3 over 2 is pi over 6. I see arc cosine of 1/2. I'll go down and look for 1/2. Pull back, I see pi over 3. Yes, I wrote pi over 3. That's good. Where it gets funky is when you have a negative. If I say arc cosine of negative square root of 3 over 2, I can't say negative pi over 6 because cosine of negative pi over 6 is going to be positive. It's not going to help us. We have to spit out something between 0 and pi. What we need to do is find pi over 6 in the second quadrant. So drawing a quick graph, pi over 6 in the second quadrant means the angle I'm looking at is 5 pi over 6. Let's try to do some simplifying. Now in all cases, trig, and by trig I mean sine, cosine, tan, secant, cosecant, whatever one I missed, cotan, trig of arc trig of x is x, always. Arc trig of trig x can be tricky. Let me show you what I mean. So let's say I have arcsine of 2 pi over 3. Well, sine of 2 pi over 3, That's a reference angle of pi over 3. It's positive, so it'll be arc sine of square root of 3 over 2. But I need to spit out an answer in the first quadrant, and 2 pi over 3 is not in the first quadrant. Arc sine only spits out numbers between negative pi over 2 and pi over 2. So I have pi over 3 is the arc sine of the square root of 3 over 2. Let's check another one. Arc sine of negative 5 pi over 6. Well, negative 5 pi over 6, the reference angle is pi over 6. The sine of that would be negative 1/2. Arc sine of 1/2, well, if it's negative, I need the negative angle, and 1/2 means my angle is pi over 6. So arc sine of negative 1/2 is negative pi over 6. Let's try one with cosine. Arc cosine of negative 5 pi over 6. Well, negative 5 pi over 6 is in what, the third quadrant, so cosine is negative. A reference angle of pi over 6 means I'm going to get square root of 3 over 2. Arc cosine of negative square root of 3 over 2. Well, arc cosine is that weird one. If it's negative, I have to put it in the second quadrant. So pi over 6 in the second quadrant is 5 pi over 6. Let's look at one I'm more likely to ask you to do in this class. Let's say I give you sine of arc cosine of x. I want you to simplify this. Well, keep in mind that arc cosine of x is an angle. So let's call it theta. What do I know about this theta? Well, I know that cosine of theta is x. So I'm going to draw me a little triangle with my theta down there. Remember, cosine is adjacent over hypotenuse, so I'm going to fill in the x and the 1 appropriately. Using the Pythagorean theorem, I can get the third side. Well, x squared plus this squared equals 1 squared. So this side has to be the square root of 1 minus x squared. Now, keeping in mind, what I'm looking for is sine of arc cosine or sine of theta. Now I can just read it off the triangle. Sine of theta is square root of 1 minus x squared over 1, or square root of 1 minus x squared. This is a better example of the kind of manipulations I want you to be able to do with the triangle. We needed to start with the basic definitions, but this is the manipulations we want to play with. And we'll do more in class.